So, in the definition of CF, skin friction, coefficient of skin friction is equal to tau W divided by 1 over 2 rho V square, CW tau W divided by 1 over 2 rho V square. This is the definition of skin friction coefficient. Now, substitute the value of tau W from the previous equation, which was developed by the basic concept of summation of fx is equal to 0 for given control value, right. So, after substituting we get this equation del P star multiplied by A SL 1 over 2 rho V square, right. Now, we are defining another term which is known as hydraulic diameter. This dH is known as hydraulic diameter, and hydraulic diameter is defined as 4A 4 into area, projected area divided by S perimeter, 4A divided by perimeter S, right. So, in case of the pipe, the hydraulic diameter dH will be diameter of the pipe, but in case of other section, any other type of section or any other type of section, we can find out the area. This is the area multiplied by perimeter we can find out, and this will give us the hydraulic diameter, right. So, by defining the hydraulic diameter, the CF may be written in the form of the given equation 1 over 4 dH divided by L del P star divided by 1 over 2 rho V square, right. So, in this case, this CF is defined as fanning friction factor, but if we remove this term 1 over 4 from this equation, then the friction factor which we get with the help of this equation is known as Darcy friction factor. So, 4 CF 4 multiplied by CF, if it is written as F, which is known as basically Darcy friction factor, but most of the time it is used as a friction factor. So, F is equal to dH divided by L del P star divided by 1 over 2 rho V square, right. So, in a more simplified manner, to do away with this H, this F is equal to D divided by L del P star divided by 1 over 2 rho V square, and for pipe flow, because diameter of the pipe is equal to dH. So, F is equal to D divided by L del P star divided by 1 over 2 rho V square, right. Now, we will write this equation in another format in terms of head loss. This is the pressure loss, del P star is the pressure loss. Now, we know that pressure may be written in terms of the head of the fluid, P is equal to rho G into H. Rho is the density, G is the gravitational, and H is the head, corresponding head for this P of that fluid having density rho. So, del P star also may be written in terms of delta H, right. So, we will write this equation in the form of delta P star is equal to F L divided by D 1 over 2 rho V square. Now, in terms by using the pressure equation, this del P star may be written as HF with the help of this concept, that del P star divided by rho G. We know that del P is equal to rho G del H of this fluid having density rho, right. So, del P star divided by rho G is equal to basically delta H, or delta H is basically head loss. When fluid is flowing, let us say in this pipe, and this length is L, and if we put piezometric tube here and piezometric tube here, in this piezometric tube this water rises up to this height. In that case, depending on several parameters, in this piezometric tube this water rises up to this height. If we find out the difference of these heights, then this height is known as head loss, HF, right. Here pressure is more, here pressure is loss. So, this loss of pressure is in terms of the head loss is basically this thing, that if we put a piezometric tube here, this water rises up to certain height. If we put piezometric tube here at a distance L in a pipe, then the water, even if we have a horizontal pipe, this water rises up to certain height, and difference in height in these two piezometric tube will be HF, right. This is the meaning of head loss between these 2 points. So head loss may be written as FLV square divided by 2GD. This is the equation, very generalized equation. F is friction factor, L is the length, V is the average velocity, V square divided by 2GD. So with the help of this equation, we can find out the head loss for any flow problem. And why we are so much interested in finding out the head loss? Because to design any pipe flow problem or any flow problem, we need to know that how much energy is lost. On basis of this information HF, we can decide the size of the pump, size of the compressor, etc. required to maintain that flow rate, right. So that's why it is important to calculate HF. So this HF is required for designing any pipe flow problem or any type of fluid flow problem in which we need to supply the external energy for maintaining that flow rate, right. So now in this equation, length is known to us, velocity we can find out. If we know the discharge, then discharge is equal to A into V. With the help of this formula, we can find out the average velocity. We know the diameter of the pipe, only unknown is F. So how can we use this formula? Because we don't know F, friction factor. If we are using this formula for laminar flow, and wherever we are using this formula, we have fully developed flow. What is the meaning of fully developed flow? We have discussed this thing in the last class. Whenever the velocity profile in the pipe or any shape remains constant in the downstream side, then that portion of the pipe is known as a fully developed flow. So for fully developed laminar flow, we can find out the friction factor with the help of Hagen-Poiseuille equation, and this can be calculated with the help of Hagen-Poiseuille. Hagen-Poiseuille calculated this F is equal to 64 divided by Reynolds number. With the help of this analytical relationship, we can find out the F. We know the Reynolds number is equal to rho V d over mu. Mu of the viscosity of the fluid, V is the velocity, d is the diameter, rho is the density of that fluid, right. So he analyzed it with the help of the control volume approach, but the same equation can be discussed with the help of Navier-Stokes equation also, and then we will reach to same solution. So same solution can be done with the help of this dynamic equation, which is known as Navier-Stokes equations. We have not discussed this, but we have discussed the control volume approach, and we found out the F is equal to 64 divided by Reynolds number for laminar flow. So if Reynolds number is less than 2000 or 2100, then we can use this friction factor and substitute here and can get HF. But generally we know that in engineering applications or in nature, the fluid flow is of turbulent in nature. So in turbulent flow, we don't have the analytical relationship for finding out the friction factor. So for that, we know that this friction factor can be calculated with the help of the Moody chart.